What I'd like to start with is talk about, well, last time I showed you about the idea of using combinators as a mechanism of building systems out of pieces that are basically like blocks, like, what's these little things be called? Legos. Legos, yeah, like Legos. They fit together according to a standard pattern. Yes. And today I'm going to do that in two ways. First, I just want to show you how you make an evaluator like that. Okay? An ordinary evaluator that's basically doing one stage of compilation for the purpose of eliminating some of the work that an evaluator does. Okay? We're hoping that maybe Chris can get around to some point showing you how you could then shove symbolic variables through such a compiled code to obtain something that's monolithic and therefore can be compiled much more, even more efficiently from that point, but we're not going to do that today. Yes, Chris is having some problems. The other thing I'm going to do is then show you how by a small transformation of the combinators that does not change any of the syntactic phase at all, okay, all of a sudden you can get the power of backtracking built into your language. Okay? The combinators will change structure, and therefore certain searches will become implicit. Okay? And that's a lot of fun. And if I have time later at the end, because although that stuff I'm telling you could be done in any language, that is, in any language that you have. Okay? Well, I suppose almost any. I think it would be hard to write in Perl. No, actually, that's probably not true. Probably Perl is very universal too. It's just a one-liner. But in any language you have, it's possible to write an evaluator for any other language. That's because of the universal machine theorem. And it's pretty easy, actually, because you've seen the basic structure of one. And if that's the case, you can always lift yourself out of whatever muck you're in by making whatever language you like. That's what I'm really trying to show you there. But the other end of this is sometimes if you have a language which is sufficiently competent, then you can do something called embedding, where you can grab all the structure of the original language you're in and take advantage of it, as well as extend it in some non-trivial ways. And I'll show you that. Okay? So to begin, to get back to this, I finally have decided I think I can make this computer sometimes work and sometimes not. This is, of course, the dispatch for the beginning of an evaluator, we thought. Well, it looks sort of like that, except this is different. Eval is no longer one piece. It's actually two pieces. I'm going to analyze the expression, and then afterwards I'm going to execute it by running it, by calling the resulting object, which is called an execution procedure, on the environment. The environment represents the information that's not intrinsic to the expression or its structure, but rather to the meanings of the names in the expression. And so, with the exception of a few chosen keywords that, for example, over here we're talking about them, or special forms, we have quotations, variables, assignments, definitions, etc., which we, of course, could do by a generic mechanism, and, of course, it really should be generic. Okay? It's just that the number of lines doesn't fit anymore on the screen to do it that way. So for each kind of expression, there is a handler, which is the evaluator, sorry, the analyzer for that expression. And what its job is to produce an execution procedure, which is in fact a combinator type structure in the sense that all execution procedures are exactly the same shape. And those shapes will be composable to make bigger things. So some of the devices here, like if, will be composing several combinators to make a bigger combinator of the same shape. Okay? Because of course the overall goal here is not so much, although I am very interested in you feeling good about making your own language as you need it, the other overall goal is to reinforce this idea that by making a certain kind of standards for the input and output of little pieces that you can paste together, you can make bigger things that look exactly the same as the smaller ones, and that there are glues that put these together nicely. Okay? So let's take a look at some very simple ones. Okay? Well, if I have a self-evaluating expression, then independent of what the environment is, all I need is the expression. Okay? It's like express such a thing might be the number the numeral 3.5 produces a number which is in the way computers are represented the same as the numeral expression. Okay? Quoted expressions, quoted expressions extract the text. Okay, but we do that at the time before we actually have an execution. This is the execution procedure. It does nothing other than take an environment and return the quoted value. Okay, that is the text of the quotation. But notice that the analysis, this is the analysis that's out here, okay, and it's done before any execution. So, in fact, as much analysis as I can, I might want to do early. So this is kind of a stage of compilation. That's a rather nice stage of compilation because it's separating out again the concern of syntax. Right? And indeed, for a variable, okay, well, I'm going to pick up the variable's value. Okay, that's the simplest kind of execution procedure again. Assignments do nothing very exciting, but notice this: an assignment might be to do to assign some variable to some value expression. Okay? So an example might be set x to the sum of y and z. Okay? That's something you might see in your nice Fortran program, okay, in some other syntax. Okay? And what happens here is that we pull out the assignment variable, which is presumably the x, and the assignment's expression, the expression part, that's this, has to be analyzed because it's a program to be executed later. Okay? So this analysis, whatever it is, this might be an arbitrarily complicated expression, including procedure calls to things that you don't know about and conditionals and all sorts of other things like that. That analysis is being done here, and then we produce an execution procedure in this environment. We produce an execution procedure which sets the variable's value to the result of calling the analysis of the assignment value on the environment. See? So that's a nice breaking up as well. Okay? And here is what if is the first really interesting one. Okay? Because what's happening is if, of course, again is if n less than n2, the result is say n, otherwise the sum of Fibonacci of n minus 1 and Fibonacci of n minus 2, right? An example of a little if. Okay? Well, there are three expressions: the predicate, the consequent, and the alternative expression. Okay? And each of those needs its own analysis, and all of those can be done. Okay? Over here, we're seeing the analysis of the predicate, the consequent, and the alternative, none of which depends upon the environment. Analysis doesn't depend upon that. It's purely syntactic analysis. But at the time of execution, we pass in an environment and call the predicate procedure on the environment. If that turns out to have a true value, then we call the consequent procedure. Otherwise, we call the alternative procedure. Okay? So what's happening here, of course, is I'm gluing together analyzed subexpressions, and this has the same shape as any one of those other combinators we see. Okay? Of course, the shape is completely simple here. We'll get to more complicated ones later, but the shape is in goes an environment, out goes a value, and this is an execution procedure. More complicated thing, well, actually, these are pretty simple. So, for example, for a lambda expression, that's the specification of a procedure. Okay? A lambda expression, for example, here's one that I will about to construct here. No, fib equals, sorry, that's not what I meant. Lambda of n. So if I have a lambda expression, that's a specification of a procedure to be executed later. It has various parts that have to be worked out. The whole body can be compiled early. Right? It can be analyzed at least. So the syntax could be extracted. So here we're going to analyze the body. The body turns out to be, in general, a sequence of things. I can do anything, a bunch of things that involve assignments and then return a value. And that's legitimate in Lisps. Okay? And so that's what this is doing. And there are lambda parameters that are pulled out. And I just have to make a procedure which contains the variables, the body of the environment, the compiled body, and of the procedure, and the environment in which the variables that are free in the body will be evaluated, will get their values. Okay? A sequence of expressions is made out of various pieces. If I have two execution procedures, then I can make an execution procedure which glues them together very simply sequentially, because indeed a lambda expression may have a sequence of expressions in it. Okay, so this is an execution procedure that takes an environment and calls the first procedure and the second procedure in order on that environment. Okay. However, of course, there may be any number of these, so I have to glue these together. So I have a little loop that glues these together. Okay. But before any of these things are run, of course, okay, because this is just making up an execution procedure, okay, I have to run this loop. First, I want to analyze all the sub-expressions in that sequence. And so this is very, very pretty. I love this kind of code. Okay? It simplifies everything in the way you think, and it's indeed one of the steps in making a nice compiler, okay, that you can use. Applications are, of course, something just like fib of minus n1. That's an application. And we have to find out what we have to do is first get the operator, okay, and all of the operands, and I want to analyze each of those. Okay, this is in a call by value or applicative order language. I have to do that. I'm going to have to do that anyway. Actually, in normal order language, I would do the same thing, but I have to attach the environment differently at different times. Okay? That's what happens there. And so here's the execution procedure for that. It picks up the environment, and it executes an application which is the procedure, the procedure's procedure, the procedure that computes the procedure, okay, which is the result of analyzing the operator, part of the expression. Okay? That one applied to the result of applying each of the argument procedures to the environment. Okay? That's what that is. Okay? And an application is applied by, again, this should be generic, as I say. Okay? But an application is operated on by deciding whether the procedure given and handed in is a primitive one or a compound one, in which case we do exactly what we've done before. Okay? Except for one thing, which is that the proc we're seeing here is actually something whose procedure body is a procedure which gets called, because that's the result of having done an analysis rather than the previous case, the result is just an extracted piece of text. That's instead of being an evaluator, we have here a compilation phase, which is happening first. Okay? Okay. So are there any questions about this yet? Yes, sir.
Is there a way to compile away lexical
references? Absolutely, there certainly is. Because this is a lexical language, I mean, it's easy. You make what's called a display. This was invented, I suppose, at the time of Algol. It's a data structure which is easy to build, okay, and that has a set of numbers. It has a numerical index saying that the particular variable you're interested in is in frame 3, variable 2 of the display, and that could be thought of. Now, however the system builds those things, it could in fact optimize those. So, for example, those could be built as some simple two-dimensional indexing array of some sort. It could be built in other ways as well. There are a zillion possibilities, okay? But you no longer have to refer to the name of the variable. And you can, by analysis, you can determine all the variable positions ahead of time because it's lexical. This would not be true in a dynamic thing like APL or traditional Lisp. Or are there other languages that have dynamic variables in them? I don't remember. There are things like C where it's ill-defined, and Java, which takes 3 weeks of understanding the book to figure out what it does. But I think in the case of relatively simple languages like a Lisp, these days Lisps are lexical.
How about parallel assignment?
Excuse me?
How about parallel assignment?
Parallel assignment. Now, what do you mean by that? You mean you're going to evaluate a bunch of things, and then you're going to assign them to a.
So if x is y and y is x plus y.
Well, that you do with let in the traditional Lisp languages. Okay. Why is that?
I was thinking more like a parallel set.
In a parallel implementation, you certainly can have parallel implementations, and in fact, people have made many parallel implementations of Lisp languages. And indeed, parallel assignment is one of the things you normally build. I just haven't put it into this one for illustration. Okay? Yes, sir.
It looked like from the description of things like analyze if that the way it's currently generified, you wouldn't be able to detect, say, that the pproc was actually a procedure that didn't really depend on the environment. It had some constant value. Let's say it was always true.
Well, that's fine. Then what it will and the analysis will produce is the
procedure that returns true.
Right.
But what you would maybe this is not that critical in any real environment, but you would like to not produce lambda.
Okay.
And
you're worrying about optimizing out by procedure integration of the resulting combinator pile. That's something that Chris was actually going to tell you about today, but didn't quite finish it. Okay? Yes, because that can be done, and the way you do that, just to say the way you can do it, is by doing what's called partial evaluation, where you install literal arguments, and you pull them through as if by doing algebra on them, okay? And then of course simplifications occur in the standard way, okay? Some of which are constant folding and dead code elimination and that sort of thing. Okay? But that's another stage in compilation. Okay? There. Does that help?
Yeah.
Are there any other questions at this point? Okay. So now what I'd like to actually do is pull a fast one on you and tell you about a rather nasty kind of programming, which involves Mr. McCarthy's AMB operator. Okay. How many of you have ever heard of that? Okay, good. How many not? Okay, so that's an equal. Okay, this is a nice thing. It allows you to do a number of things that are pretty spectacular. In particular, what it allows you to do is it allows you to write an expression which represents one of multiple values, but you don't know which one it is. Okay? And as a consequence, it allows you to build what's the equivalent of non-deterministic automata in an order programming language. Okay? This was invented probably by McCarthy in the original paper called, I forgot the name of the paper. It was the one where Lisp was actually introduced. Yes, thank you. That's the name. That was 1958, right? Yes. And that's, say it again out loud for everybody.
Computation of symbolic expressions by machine.
Right, that's right. Okay, thank you. Something like that. Okay, very nice paper where he introduced almost everything that's useful. Okay? He, by the way, for those of you who don't know, he also invented the if-then-else statement for algol. Okay, before that, Fortran had the three directed if, which is less than, greater than, or equal to. Okay, and McCarthy didn't quite like that. So what this is actually a very nice thing. Okay, you can write down a procedure, actually lines like this: 1, 2, 3. The possibility, the question of I have an expression which is either 1 or 2 or 3, and I don't know which, and I have another expression which is either A or B, and I don't know which, and I can make a list of that. That's a list of, therefore, some choice from column A and a choice from column B, right? Okay, and then I'm going to write that out. But here's something that has no choices at all, right? As a consequence, it's a failure. And as a consequence, this was not a happy expression, so it will backtrack and try something else. Okay, and so what I get is the printout of all the possibilities in this case, until I run off the end of the set of possibilities. Okay, so AM is a neat thing. For those of you who like the mysticism of quantum mechanics, I'm going to say something that's sort of fun there. Consider the following. The double procedure is the procedure of one argument x which adds x to x. Okay? Now, what if I say double of amb of, say, -1 and 1, and amb, no, that's it, that's enough, just that's it. Fine, good. That's right, it's only one possible thing there. Okay? What are the possible values of this? It depends upon the order of evaluation. Okay? If I do applicative order, that means I evaluate the arguments first, and then do the procedure. This is applicative. Then the two possibilities I get out of this are either -2 or +2, right? Because I could only get a -1 or 1 out of this, and I could then double that, so I get a -2 or a +2. That's two possibilities, each happening with frequency in general, if you believe that that's important, of 1/2. Okay? If I'm in neural order, which means I'm doing essentially call by name, okay, in the traditional algol sense. I mean, I don't evaluate this argument until I need it. But there are two places where I evaluate it, and therefore I get the choice twice. Okay? Now there's some intermediate things like call by need where you have memorize the result and things, but I'm not trying to look at all the details here. But in that case, I get -1 is possible, not -2. Sorry, -2. I can get 0, and I can get +2. Okay, and I get these with the frequency 1, 2, 1, whereas I get this with the frequency, or say 1/4, 2/4, 1/4, whereas this I get with 1/2, 1/2. So for those of you who believe that quantum mechanics specifies the way the universe works, which I'm not surprised, it seems to be true, then that tells us that the choice in Lisp is correct, and it went by multiplicative order because there's interference, okay? Because of the idea of identity. But that's, okay. You may decide whatever you please about that. Okay. So, yes, there are a number of interesting things you can deduce about the universe from some numerological things like this. Sometime I'll show you some others. Anyway, so here's the kind of thing you can do with AMP, and then I'll show you how you implement this by a change in the structure of the combinators only. Okay, that's fun. Okay? So for example, supposing we want Pythagorean triples. Okay? So if I have an integer between I have some integer between some low number and some high number, I, and I'd let j be an integer between I and high, and let k be an integer between j and high. Okay? Okay? So I get 3 integers. I'm going to require that the sum of the squares of I and j equals the square of k. Okay? And if I pass that test, then I'm going to produce a list I, j, and k. Okay? But only things that pass that test can get out of can come out. Okay? Now, what it means for an integer between low and high, how do you choose one? Well, it had better be the case that low is less than or equal to high. And the answer is either the low value, or it's an integer between low plus 1 and high. I don't know which. Okay? So this is going to do the right thing. Require is just something which says if the predicate is not true, this predicate is not true, then fail. Okay? So if I run this program, I'm going to have I'm going to do a right line. I'm going to do a right line of the Pythagorean of that triple, and then fail, so I get all the possibilities. Okay, and you see what I get are in fact the Pythagorean triples having the right specification. Okay, so there they are.
What on the A and B is there?
And for ambiguous. Okay.
Are there probabilities associated with choices?
Not in the way I've shown you right here. Usually here it is that in the way I've written it, it's a left to right choice in some order, in the order of left to right. And so if it tries the first one, if that doesn't work, it tries the next, and so on. You could begin to extend it in the ways of probabilities. Alexei has done so in a project for not project, was it a project for a class? Yeah, it was a project for a class a couple of years ago. What else? Those are sort of things that you may choose to do. And then there's the interesting question of whether or not you might want to do things that are symbolic and analytic with this as well. That's pretty interesting. Okay. But remember, everything is mutable. We can elaborate as much as we want. That's the whole idea of this whole sequence of talks, is to show you that you have power that you may or may not realize. Okay? The power is to change things. You can write whatever language you need. You can make whatever structures you want. But don't. The important thing is not to get into a hole, to program yourself into a hole where you can't do that, where you've sort of gotten committed to you have an ontological commitment, say, an object-oriented model. And that's all right. You can use it when you need it. Okay, you get a functional model or a logic programming model or a whatever. Okay, each of these is good in its appropriate time, but not appropriate for every problem. And the worst thing is to get so committed to any one of these models that you can't also, in the same piece of code, use something else for the appropriate part of that. Okay? So that's actually the real secondary level thing. There's a famous set of logic puzzles that many of us have played with. This is a typical one it came from a book by Dinsman in 1968, and we use it in the SICP book and things like that. Baker, Cooper, Fletcher, Miller, and Smith live on different floors of the building that has only 5 floors. Okay? Baker does not live on the top floor. Cooper does not live on the bottom floor. Fletcher does not live on either the top or bottom floor. Miller lives on a higher floor than does Cooper. Smith does not live on a floor adjacent to Fletcher's, and Fletcher does not live on a floor adjacent to Cooper's. Where does everyone live? Okay? Now, it can be thought of as a search problem. Okay? And of course, there are dumb ways to write the search and smart ways. I'm going to show you a dumb way. But in any case, it's going to work. Okay? Because you see, the great idea, and before I go any further, I'll show you the great idea. The great idea in this is something like this. Okay? The great idea is this. A lot of processes can be thought of as being made out of 2 parts. Something called generate and something we call test. Okay? And so You know, you can think of something that generates a set of possibilities, and there's some channel, and there's something that tests them. Okay? And only some things come out that are good, the good ones. Okay? And there might be some very complex process in between, by the way. There might be something that's manipulating the possibilities. Okay? And that happens very often. So, for example, it occurs in choosing appropriate paths to take something to Mars. Okay? There are a very large number of plausible ways to get to Mars by appropriate burns of rockets at the right time. The difficulty is that some of these are expensive and some of them are cheap. Now, none of them are cheap. All of them are expensive, but some are more or less expensive. Okay, and the reason is because you can take advantage of the behavior of the rest of the solar system. You can do things like use the fact you can take a boost by taking a little energy and angular momentum out of the motion of the Earth. Okay, we'll never notice it, but the satellite gets slingshotted if you pull it by in the right way, and things like that. Okay, now it's hard to a priori figure out what these are, what all the possibilities are. And so one thing you can do is generate lots of possibilities and then say which ones look good. You have to work out the details. But the working out the details, this part, is an immensely complicated and very expensive process called numerical integration. Okay? And if you do it to the accuracy required for dropping something on a certain square foot of Mars, that's going to be a terribly complicated process. Okay? Because you have to take into account the masses of some of the asteroids, okay, and all sorts of weird things that in the case of a light type of satellite, you may have to take radiation pressure from the sun, drag from the solar wind, things like that. Okay, so it's a very complicated business. So this could be terribly expensive. The test may not be very expensive. The generate may not be very expensive for the possibilities. Okay, now. One thing is that this may be also a program that doesn't want to know very much about the fact that there are many possibilities. Why should the person who wrote this give a damn that this is being done in this way? It's not very interesting. Right? It's not like I want a set that has to be carried along and pulled through everything. It's not that I want to even understand that there might be a loop structure here. Okay, supposing this part is just a separate, isolated piece, why do I have to think about that loop? Okay? So very often it's the case that it's the advantage to build a system that separates them out so that this loop that says I reject it is implicit. Or another way to think about that is from electrical engineering, which we do a lot. You can think of, well, some things are done best by having a noise generator and then a filter. Okay? And what you get out is an interesting, pink noise of the right type or something like that does exactly what you need for some job. For example, something that does dithering of a CD, the bottom bits of a CD. And you have to do that by something like that. Of course, there are deterministic algorithms doing this as a digital process, but I'm thinking about this as an analog thing. Okay? So that happens too. Well, biology does this all the time. What you're looking at is the thing that supports the inside of a cell. This is a picture I got out of Wikipedia, and I accidentally forgot to put on it the attribution, so I apologize to the Wikipedian that I did that. But the point is that these are microtubules. Microtubules are a particular protein structure that appears inside of cells. It's a polymer that's made out of individual protein units that are big proteins, and they polymerize themselves from some centrally organizing part of the cell. But they grow out in random directions, and then they contract, so some of them they're almost all unstable. But the interesting thing is that there are, on the surface of the cell, there may be stabilizing spots. Such if a microtubule happens to hit one of those stabilizing spots, which may be determined by the environment, it may be determined by its neighbors, other cells nearby, okay, then it sticks, and that becomes a rigid rod producing structure and making the cell have a shape. And that's why cells in our bodies have shapes, things like that. Okay? So, but the neat thing about that is it's separating two parts. The microtubules are generated by every type of eukaryotic creature. Okay? That means even yeasts produce them, I think. Okay? But the wild thing is, of course, we have all these different shapes, like neurons and skin cells and things like that. And they all have different shapes, and the shapes are produced independently of the method of holding the shape if you have it. The microtubules are the scaffolding structure, which is generated by generating, and then testing is what determines the shape. And that's a neat thing. Okay, so here we have even biology's happy with this idea. Okay. So let's go back to this. Okay, well, how do we solve problems like this? By generate and test. That's sort of one of the ways of doing it. And so we can write down a program that looks like this. Okay? Baker's floor is either 1, 2, 3, or 4, or 5. I don't know which. And so is Cooper's and Fletcher's and Miller's and Smith's. It had better be the case that they don't live on the same floor according to the plan. Okay, and I might have to show you how to write the distinct predicate. Okay? And it's also required that the various other constraints, Baker is not on the 5th floor, Cooper is not on the 1st, Fletcher is not on the 5th, and Fletcher is not on the 1st. Miller's is greater than Cooper's, and the Smith and Fletcher are not adjacent, and Fletcher and Cooper are not adjacent. Okay? And it turns out this is adequate for giving it a unique answer. Okay? The answer looks like this. Oh, there's the definition of distinct and require. Baker lives on the 3rd, Cooper lives on the 2nd, Fletcher lives on the 4th, Miller lives on the 5th, and Smith lives on the 1st. Okay? So by suppressing these loops, although you can get into horrible trouble that way, because search generates exponential amounts of work. So being dumb is not, this just allows you to be dumb in another way. Okay? But being allowed to be dumb in this other way allows you to write programs sometimes rather easily that you couldn't write, that would be a harder program some other way, which would have lots of nested loops that you don't see here. You don't see them here. Okay? So if you think about it as because you want to do search, that's a bad idea, because that's always a bad idea. If you think about it as a way of suppressing certain loop structures, then it's a good idea because it allows you to simplify your code. Okay? If those loop structures would have appeared anyway. Okay? Anyway, so how do we implement things like this? Okay? So that's what I'm going to talk about right now. And the way what's going to turn out is that it's pretty simple. Okay? First, we have to have some extra special form. So somewhere in the analyzer, I have to have a definition of what kind of thing AMB is, and I have to say that there's going to be an analyze AMB expression somewhere in the dispatch that could be done by a generic operation that's making the analyzer a generic operation. Okay? But more interesting, the execution procedures are going to be different. The execution procedures, instead of just taking an environment, they're going to take three things. They're going to take an environment, a succeed continuation, and a fail continuation, or what Chris said yesterday, a win and a lose continuation. Okay? The succeed continuation is what you call when you have an answer that you want to try out, a proposal. But you pass along a complaint department, which is the appropriate fail procedure, such that if whoever you gave this answer to doesn't like it, he can complain by calling the fail continuation. Okay? Secondly, there is a fail continuation that came in from somewhere else. For example, here's one. So you see a possible top-level call to ambival might be you evaluate some expression in the global environment, whatever that is, with a succeed continuation that produces only the value and doesn't care about its fail continuation. Okay? And a fail continuation that does nothing other than say failed. Okay? So indeed, the way to think about this is that, just to read that again, in addition to the expression which you want to evaluate with respect to the environment, you have to have a succeed and a fail continuation. Succeed is a procedure that's called to return a proposed answer, and fail is a complaint department. Okay? So let's take a look at some of these. Here's the new execution procedures. Okay? And the analysis actually is the same. I really should have factored it out. You know, that's actually dumb. I'm being dumb. There's no reason for me to have written these. These are all have the same pattern as the previous ones. So the lambda expressions should have been generated somewhere else. That should be kind of generic. Maybe Alexei will think about how to do that. Okay? Just thought of an idea. One of the nice things about writing programs is every time you write it, it gets better. Okay? And so you discover all the places you could have done a little bit better. See, what I saw is that there's a pattern I'm writing over and over again. Why shouldn't I make that abstract? So the self-evaluating things ignore the environment, but indeed it has to succeed with the value of the expression and fail being the complaint department that came in, because whoever made me do this, okay, may want to receive the failure. Okay? Quotation is similar, okay, as you saw before. Variables are similar, except that now instead of returning a value by the value being the value of an expression, it's always being returned by calling succeed. Think of that, succeed as like return, okay? And that's a nice, simple way to think about it. Lambda expressions, of course, have their same analysis they had before, but I have to succeed the result of applying of the procedure, which is the procedure of the lambda expression. Have to succeed the procedure. That procedure is the translation of the lambda expression. Okay, just review that because we're going to go to the more hairy stuff again. Okay, so let's take a look at, I suppose there's nothing very exciting here except for the fact that there's two stages in dealing with an if. Okay? An if is a little more complicated here. Indeed, I have to do the same analysis of the three parts. But the execution procedure, of course, takes three arguments. I have to call the procedure, which is the predicate procedure, on the environment with a succeed and fail continuation. If the predicate fails to be able to compute, if it finds some contradiction, if it doesn't like what it sees, which is not the same thing as returns false, if it doesn't like what it sees, okay, it may call the fail continuation, causing whatever it is that got us here to produce a new values. However, if it succeeds, okay, it produces a value, which is the predicate's value, and a failure continuation whose job it is to be something passed along to the consequent or the alternative, whichever one which will be used. The consequent or the alternative may itself decide it doesn't like what it sees, and it might want to say, give me a different result from my predicate. Okay? No, the answer is no, I don't like that. And the predicate might look at it again and say, oh, there's an alternative. You know, maybe it was false rather than true. Okay? That's a choice. So the predicate is the guy who's going to be making up the failure continuation here, okay? Which it's passing into here to allow these guys to say, predicate, I didn't like your answer, as opposed to predicate, what was your answer? Because everything's tentative now. That's sort of the nice thing here. More complicatedly, look at sequentially. Sequentially, the only interesting part of sequentially is what you saw before. It's the part that determines A and then B. Do A and then do B. And in that case, the execution procedure here says, do A with the failure that came in, the failure continuation that comes in from the call to A, call to the sequentially, okay? But when you succeed, produce if A succeeds, it must produce a value which is ignored because B is a sequentially first do A, then do B, okay? But then it has to produce a failure continuation which B may call to cause A to change what it produced or what it did. Which, by the way, means that there may be assignments, they may have to be unwound, all sorts of things like that. Okay? And we have to worry about that. Okay? The rest of this is the glue that allows you to make this into a sequentially of any number of things. Okay? A sequence of any number of lines of code. A procedure application is also similarly interesting. I have to take the execution procedure here, which evaluates the procedure, evaluates the procedure, okay, getting me that's what I call FPROC, getting me a procedure, okay, and a failure continuation because this might generate a different procedure if I wanted it, okay. That one has to get the various arguments after I figured that out, okay, and the arguments themselves, eventually I get all of the arguments. We'll look at that in a second. Okay, but that'll produce another failure continuation, which I then have to get past to the execution part, the application part, which takes the procedure and gives the arguments to it and executes the body of the procedure. Okay? But that has a failure also. So if the body of the procedure doesn't like what it sees, it might say, give me a different value for one of the arguments, and that may give me a different value for or a different argument, which may ultimately cause a backtracking to a different value for the procedure itself. Okay? All of that is chained together by these failure continuations. Okay? So you can see the chaining. It's very simple here. Again, there is the first argument. Okay, and the rest of the arguments, and they're chained together because this calls the get args recursively. So the rest of the arguments are the rest of them. Okay? And execute application is all the same as it was before, except we're carrying along the failure continuations. Okay, it's time for a break. I ran my 50 minutes, as I always do. Okay, and so we'll be back in about. Oh, you want to talk? Question? Yes.
Does this make in applicative order?
This particular program is applicative order.
Where is that fixed?
I don't know. That's what I mean by is if I had to think about it, I would. I mean, I hadn't thought about it yet. In fact, I actually have thought about it. I have a program that's a normal order version of this. But there are some funny things that go on in normal order. Okay?
That's why I ask.
Yeah, there are very funny things that happen in normal order with respect to backtracking. And I think we'll talk about that in a little while. How's that? Like in another 20 minutes or so? How's that? The problem is that it's easy to do the transformation to this program that puts it in normal order, or to add normal order procedures like I did to the previous one, the previous evaluator. That was the explicit evaluator rather than the analyzing evaluator. But the difficulty is that to predict the consequences of that are not obvious. And I'm not sure I know the consequences in the case of including AMP in normal order. Okay? There is a paper, an excellent paper by Will Klinger on this. Do we have the paper? It may be in my briefcase. Okay. It was written a long time ago. Does anybody know the name of the paper? So I don't have to dig around.
Non-deterministic call by name.
Yes,
neither by value.
that's right.
Neither by
Non-deterministic
by
by call by name is neither by value or by need by Will Klinger, and no, neither lazy or by need by Will Klinger. And how long ago was this written? Probably around 1980 or something. Yeah, I don't have it here. Okay, but that's the name of the paper. And he does a fairly hairy analysis of that question and comes to a variety of strange conclusions. Okay? So, Ty, let's have a 5 or so minute break. Okay?